day, students. Today we shall look into vibrational spectroscopy, or in the terms of its electromagnetic spectrum, the infrared spectroscopy. We shall learn what is IR spectroscopy. How do you get a spectrum from a harmonic oscillator and from an unharmonic oscillator? Now, this is the nature of the infrared spectrum that we obtain from infrared spectroscopy or vibrational spectroscopy. So, the molecules will interact with the radiation under this wavelength, under the wavelength from 6,000 centimeter inverse to 2,000 centimeter inverse, that is in terms of wave numbers. That is 6,000 centimeter inverse comes in the near infrared range and 2,000 centimeter inverse comes in the mid infrared range. So vibrational spectroscopy is the study of vibrating molecules, the study of vibration in molecules. Due to the elasticity of the bond length, the molecules will vibrate when they are excited. The vibrational energy thus attained by the molecules, it cannot be in any energy. The energy is not continuous, but it is quantized. So the molecules can vibrate only under fixed vibrational energies. The infrared spectrum obtained gives valuable information regarding the molecular structure, the symmetry, the bond strength, and intramolecular interactions within the molecule. Now, let us assume the molecule as a harmonic oscillator and study the vibrational energies from it. A diatomic molecule can be considered as an oscillating spring mass system. That is, masses m1 and m2 are connected by a spring of force constant K. Now, the distance between the two masses at equilibrium is the equilibrium bond length Req. And this is the classical harmonic oscillator model. Now, under this model, when this molecule is excited, it is given energy. It may start to vibrate as shown here. Now, being a harmonic oscillator, this bond will obey Hooke's law, which is given as the restoring force is equal to minus kx. Now, instead of x, we have the distance in r terms here. It can be written as minus k into r minus Req, where r is the instantaneous distance and Req is the equilibrium distance. The potential energy of the molecule is given by U is equal to half K R minus Req square. And the curve obtained for potential energy is as shown here. Here the curve is represented as half kx square, and instead of x we have r minus Req here. And in this potential energy, the molecule can vibrate on these discrete energy levels. Now, the frequency of that oscillation or frequency of that motion, nu naught, will be equal to 1 by 2 pi root of k by mu, where k is the spring constant and mu is the reduced mass. Now, to identify the energy of that vibration, we solve the Schrodinger equation for the harmonic oscillator, and we obtain the final relation as the vibrational energy EV is equal to V plus half h nu naught. Here, the quantum number V is the vibrational quantum number, and it can have values 0, 1, 2, 3, etc., integral values. In spectroscopy, usually we measure the energies in terms of wave numbers. Hence, by dividing with Hc, we obtained the eta V value as V plus half nu naught bar. And this is in wave number units, hence the unit is centimeter inverse. Now, in the harmonic oscillator, we saw that the graph for the potential energy is as a parabola, and the energy of the vibrational states in terms of wave number is given as eta V is equal to EV by Hc is equal to V plus half mu naught bar, centimeter inverse. Let this be equation number A. Now, for different vibrational quantum numbers 0, 1, 2, 3, etc., we get the different energy levels. So, at V equals 0, we have eta V equals 0 is equal to half mu naught bar. That is, this line is obtained. We understand that the energy is not 0 at V equal to 0. That is, even at the lowest vibrational energy level, the molecule is in a state of vibration. Now for V equals 1, we have the upper energy level of energy eta 1 is equal to 3 by 2 nu naught bar. For V equals 2, we have the higher energy level eta 2 is equal to 5 by 2 nu naught bar. Likewise, for vibrational quantum number 3, 4, 5, we have the corresponding eta values. Now, this molecule, when it is given energy, it can undergo vibration by only following certain rules, and they are called the selection rule. Now, for a harmonic oscillator, the selection rule is that the molecule can have a jump in the vibrational quantum number only by integer 1. That is, the change in vibrational quantum number can be only plus or minus 1. It can be excited to the next higher energy level, or it can de-excite just to the lower energy level. And the frequency of that transition will be eta of V from 0 to 1. That is, the molecule is absorbing energy. It is given by eta 1 minus eta 0, the energy difference between the levels. That is equal to nu naught bar, centimeter inverse. You can calculate it. It will be 3 by 2 nu naught bar minus 1 by 2 nu naught bar. That is equal to nu naught centimeter inverse. Now, for the transition from the first energy level to the second energy level, that is eta V equals 1 to 2. Again, molecule in the first energy level is absorbing energy and moving to the second energy level. The frequency is given as the energy difference, that is eta 2 minus eta 1. That will be equal to 5 by 2 nu naught bar minus 3 by 2 nu naught bar. Again, that is equal to nu naught bar, centimeter inverse. Same frequency as the earlier one. Now, for the next transition from second level to third level, that is eta V is equal to 2 to 3, we have eta 3 minus eta 2. That too, on calculation, we get nu naught bar, centimeter inverse. So for all of these transitions, the light or the electromagnetic spectrum that we see from the molecule is only a single frequency. For all of these transitions, we see only a single frequency coming from the molecule, and that is seen in the spectrum as this particular line, and that line represents nu naught bar. Now, in the harmonic oscillator case, vibrational spectra is observed in heteronuclear molecules like hydrogen fluoride, hydrogen chloride, hydrogen bromide. Here, the dipole moment of this molecule will change with the vibration. That is why we observe the vibrational spectrum. Whereas It is not observed in homonuclear molecules like hydrogen molecule, nitrogen molecule, and oxygen molecule, in which the dipole moment of the molecule does not change with vibration. Hence, it is not showing any vibrational spectrum. Now, even though we saw the case study of a harmonic oscillator, now in reality, the molecular bonds are elastic, but they do not obey Hooke's law. So, the energy of the vibrational states is given by the Morse function. It was developed by the physicist named Morse, and hence the function is termed Morse function, and it is shown by this particular graph. So at very small distances approaching zero, we see that the potential energy function is obeying that of a harmonic oscillator. It is seeming like a parabola shape. But as we move away from the equilibrium distance uh, of the molecule in these regions, we see that the potential energy does not obey the case of a harmonic oscillator. It is being shifted. It is going to almost a constant value, and that is called the dissociation energy of that molecule. So the Morse function of potential energy U is given as dE into 1 minus e raised to minus a of r minus req square. Here dE is the dissociation energy, and from that the energy of the vibrational states eta V is calculated as V plus half nu E bar minus V plus half square xe nu E bar plus V plus half the whole cube ye nu E bar centimeter inverse. Here xe and ye, they are the unharmonicity constants. And due to these constants, we understand that the energy of the vibrational states, they are decreasing and they tend to crowd the energy levels more closely. Now, for approximation, we take the term of xe and neglect the term of ye because it is tending to zero. So, the energy of the vibrational levels are approximated to eta V is equal to V plus half nu E bar minus V plus half square xe nu E bar centimeter inverse. Now, since we have the expression of the vibrational energy levels for the unharmonic oscillator as shown here, let us calculate the energy level for V equals 0. So here we get eta 0 is equal to half nu E bar minus 1 by 4 xe nu E bar. We can rewrite it as taking half nu E bar outside. We write 1 minus half xe whole into half nu E bar. So that is the value of the first energy level for V equals 0. Now for V equals 1, we have eta 1 as 3 by 2 nu E bar minus 9 by 4 xe nu E bar. It can be rewritten as 1 minus 3 by 2 xe into 3 by 2 nu E bar. Hence, generalizing, we can write eta V is equal to 1 minus V plus half xe the whole into V plus half nu E bar. Now let this equation be equation B. Earlier we had equation A, and comparing both equations A and B, we understand nu naught bar is equal to 1 minus V plus half xe into nu E bar. Okay, so the fundamental oscillation frequency of the harmonic oscillator, nu naught bar, gets replaced by the equilibrium oscillation frequency of the unharmonic oscillator. and that is having an additional factor of 1 minus V plus half. Let's see. Okay. Now, using the expression for energy of the vibrational states as eta V is equal to V plus half nu E bar minus V plus half square Xe nu E bar, we understand the selection rule here for the harmonic oscillator is delta V is equal to not only plus or minus 1, you can have values plus or minus 2, plus or minus 3, etc. So the molecule can be excited to higher energy levels and other lower energy levels also. So for delta V is equal to plus 1, we get the frequency of transition eta V is equal to 0 to 1. That is eta 1 minus eta 0. This is called the fundamental absorption line, and that is equal to 1 minus 3 by 2 Xe into 3 by 2 nu E minus 1 minus half Xe into half nu E bar. Now taking nu E bar as a common term outside, we get nu E bar into 1 minus 2 Xe. Since Xe is small, we can neglect that term, and this will be approximately equal to nu E bar centimeter inverse. Now, this transition is from the 0 to 1 state as shown here by the red line. Now for delta V is equal to plus 2. Now the frequency of transition will be eta V equals 0 to 2. That is obtained by the taking difference of eta 2 minus eta naught. This frequency is called the first overtone line, and it is obtained as eta 2 minus eta 0. So eta 2 is obtained as substituting V equals 2 in all the places for V. That is 2 plus half nu E bar minus 2 plus half square Xe nu E bar minus half nu E bar plus 1 by 4 Xe nu E bar. Now this is equal to 2 nu E bar minus 6 Xe nu E bar. This is equal to 2 nu E bar into 1 minus 3 Xe. Neglecting the term of Xe, we get it is approximately equal to 2 nu E bar centimeter inverse. And this is shown by the transition from V equals 0 to V equals 2. Now, for delta V is equal to 3, the frequency of transition is for eta V is equal to 0 to 3, and it is obtained as eta 3 minus eta 0. This represents the second overtone line in the spectrum, and it can be calculated as eta 3 minus eta 0 is equal to 3 plus half nu E bar minus 3 plus half whole square Xe nu E bar minus half nu E bar plus 1 by 4 Xe nu E bar. This is equal to 3 nu E bar minus 12 Xe nu E bar. Taking 3 nu E bar common, we get 3 nu E bar into 1 minus 4 Xe. Neglecting the term for Xe, it can be approximated to 3 nu E bar centimeter inverse. And the transition is from V equals 0 to V equals 3. Now, at room temperature, the population Nj of the ground state E naught is highest, whereas the population Nj of the first energy level E1 is 0.01 percentage that of the E0 level. It's a very small fraction. Now, when we heat the sample, let us assume that the sample is heated to 600 Kelvin. The number of molecules in the higher states will become more. That is, the population Nj of E1 becomes 0.09 percentage that of E naught. It is almost equal to 0.1 percentage of E naught. Now this makes transitions at higher levels possible, and these transition lines in the spectrum are called hot bands. That is, for delta V is equal to plus 1, we can get the frequency of transition from eta v equals 1 to 2. So it is calculated from eta 2 minus eta 1, and it is obtained from 2 plus half nu e bar minus 2 plus half square xe nu e bar minus 1 plus half nu e bar minus 1 plus half square xe nu e bar. Now this is equal to nu e bar into 1 minus 4xe. Approximating it, we get it to be approximately equal to nu e bar centimeter inverse. And this is the first hot band. It represents the transition from V equals 1 to 2. Similarly, we can have hot bands for transitions from 2 to 3 or 1 to 3 also. Only at higher temperatures do we see this line in the spectrum. The intensity of the line hot bands in the spectrum will increase only at higher temperatures. So this was about the vibrational spectrum that we obtain for an unharmonic oscillator. That's all for today's session. Thank you.